And I give you one in 5 minutes before, okay?
Okay. Okay. So this morning I heard that we are living in a boring universe, isn't it? But I can assure that our work is not boring. It's exciting and stressing because we are stressed a lot to produce the product. So then I will give you some information, an overview of the pipeline that was applied to produce the maps that's being delivered. And this pipeline at the LFI and HFI level was a really common work because it's not easy. Data is not easy to understand, and the creation of the pipeline was very difficult. So in few words, this is a very overview of the slides. I will give you some information regarding the data processing overview. So how we data, how we transform from telemetry, from housekeeping until the TOI, until the timelines. So then how we do the map makers, and then regarding which kind of test we apply to the maps to understand if we are doing the things correctly, if there is bug on the pipeline, or if our results are, let's say, consistent with what respect we expected. So Planck was launched in May 2009, and the maps that we delivered are the maps that has been produced using only the first 50.5 month observation. But remember that we already have a lot of data. HFI was switched off on January 2012, and far beyond what was the nominal period. And LFI is still observing. As in today, we're still getting the data. I wrote here that we are OD 1420, but if I remember correctly, it should be 1423. So we will reach probably with LFI 8 entire survey. At the moment, you have only 2.5 surveys. No, see. Okay, yes. Okay, regarding the pipeline, the processing, the two DPCs, I mean, data are processed by the two DPCs independently. And we adopt a kind of same schema. Both the DPC adopt the same overall approach. We divide the processing in 3 levels, level 1, level 2, and level 3. In the level 1, what you do is getting the data from the satellite, from the MOC, from the Mission Operations Center, in a form that is a packet. So you decompress it, check it, and so transform and store it in a database. And so then you go to the level 2 that is responsible to synthesize the information, to start creating the instrument model, the RIMO, and calibrate the data, flag the data that you are, considered to be not useful for the science, and then store it in another database. So go to the level 3 that is more scientific oriented. Each step is internally validated very strongly. We apply a very strong validation process. And you should note also that the pipeline and the entire process was developed by different people with different ideas, with different nationality, in a different way. And so these are the very strong value of cross-instrument validation that you will see in another talks today. And I will show only one slide on that. Okay, this is an overview of the pipeline. I'm not going in deep on that, or otherwise I will talk for a lot of time on the LFI pipeline. So this is the level 1. These are the tasks mainly for the level 2. We have, as HFI 2, a different pipeline for the detector pointing. Understand where is the sample on the sky. And so then we finish the level 2 pipeline to go to the level 3 with the map making. HFI is a very similar structure. This is more detailed, in which you see this is the level 1, level 2 part, so then the level 3. And what they do is, as in LFI, they clean the TOI before going in the map-making process, before calibrating it. Okay, one important element that level 2 pipeline do, level 2 and level 1, is to flag the data. I mean, not all the data are usable to do science because you are in maneuver, you had problem with the instrument and so on, and you should set up a kind of procedure to flag the data that you believe are not at the science requirement level. This is a table that summarizes at the LFI level the amount of data that we are losing, that we are not using. You can see that we are not, this microphone, sorry, you are not getting me, okay. Yeah. Better now, yes. I shall stay there. Okay. Okay, you see that we are missing about a very negligible amount of data, 0.000. So, and some anomaly has been detected in LFI that has been due to some what is called gain change, and is about 1%, and we are losing about 8% of the data, not losing, due to maneuver. Now we are thinking to try to use that. In HFI, most of the flag data are due to the glitches. The glitches are something that are caused by hit of cosmic ray, and a special processing has been identified, has been created to flag and to process those data. Okay, now you have flagged the data. The next step is to identify where your beam are in your focal plane. So what we call as the beam reconstruction. To do that, you use the Jupiter transit for LFI and the Mars transit for HFI, and we was able to reconstruct our focal plane until minus 20 dB for LFI, minus 30 dB for HFI. This is the LFI representation of the focal plane. This is the HFI representation of the focal plane. So then what do you do with this information on the beam? You have to understand very well where the pixel, where your sample is on the sky. So again, using this information on the focal plane, we use two different procedures. We have in any case a procedure at about 0.5 arc mean to identify where we are looking at. And in the case of HFI, it was used a model provided by the US team called the PTCore that is model the behavior of the pointing, putting some discontinuity. So it modelized the pointing. In case of LFI, we just used one discontinuity. We use a flat model. And at the final, we test that, and they are at the same level of accuracy. Using the detector point, the story of the detector point is not yet finished. You have to create another element that was provided by the US team, is the effective beam. So the effective beam tells you how the beam is really on the maps that you will use for your products. So this, this is used, the effective beam is really the products that is used by the point source scatter, is the ones that is used for the beam window function at the spectra, the power spectral level. Then, okay, so you have the detector pointing, you have the beam, you flag the data. Next step is to try to understand the noise of your data. In LFI, the noise was estimated at a level of a timeline because we need the value, the white noise, to be included in the map-making process. To do that, we apply a kind of Monte Carlo Markov chain approach, and this is an example of all the spectra that we obtain dividing the data in a chunk of 5 days. You can see that this here of deviation, this is due to the after the suction cooler switchover. HFI use, in any case in LFI, we test also the results of the white noise, checking the level of the white noise at map level, subtracting them, as HFI is doing. And the value obtained at the level of TOI with respect to the maps level are very in line inside 1%. HFI exactly is doing that. So using this half-ring maps, you can estimate the value of the white noise map level. And these are the spectra. I can put these are the spectra of the half-ring maps. So you can see that these are mostly flat here due to a very good low-pass filter that has been used in the TOI. So then, now you have all the timelines, all the information, and now is the big step. So calibration. Calibration is one of the most important elements in your pipeline. Let's transform your engineering unit in physical unit like Calvin Wall. And the approach.
Reception is not good, so.
Okay.
Hello? Yeah. Okay. Now let's try to use the ice cream. Okay, so what I said is that the calibration is one of the most important elements because this is transforming your engineering unit in physical unit. The approach between LFI and HFI was very similar. In a few words, this is the LFI element of our calibration pipeline. We use the WMAP number of the dipoles, so we, pass through the hour beam, so we saw the dipole respect hour beam, and so we then fit it with our data, with the real data. So we then apply an iterative algorithm, and at the final, we apply a kind of adaptive smoothing filter to taking out, to reduce the statistical noise. The accuracy that we are obtaining are very, very good. For the 30 gigahertz, 0.82%, for the 44, 0.55, and the 70 gigahertz, 0.62. HFI, for the low frequency of the HFI, use a very similar approach. So they compare the measured data against the expected signal from the solar and orbital dipole, and this yields 3 parameters per ring. So then they applied to an iterative process, and this gave a relative variation of about 0.2%, unless a systematic is still there. For the higher frequency, the calibration is based on fitting the HFI data on Neptune and Uranus. And this gave to planetary emission models. These are an absolute accuracy of about 5% and a relative accuracy of 2%. So then you have your calibrated, and so what you have to do is to create the maps. In case of LFI, calibrated TOI together with the detector counting are fed in the modern map making. That's what's being provided by the Finlandian guys. And the code is a maximum, work as a maximum likelihood fashion, and is able to, to estimate a baseline, subtract the baseline from the maps, and create the maps finally, simply binning the results to a map. In HFI, they are projecting the data. They process the HLPX ring with TOI into HLPX maps. So they find individual rings and created by the averaging filter and baseline subtract TOI into HLPX. So those rings are used for the photometric calibration, and then they calibrate the ring maps that are combined with the last square, the strapping procedure. The maps that we produce are really a lot. We deliver only a part. We produce map at the level of single OR, single detector, and whatever. That was very useful for the null test inside the DPC. And we produce also for LFI DPC for internal use the low resolution noise covariance maps. And HFI, together with the normal map, produce also maps with the zodiacal light removed as a first attempt. Another key element is to try to understand how the systematics is affecting your data. So we spend a lot of time trying to understand the systematics. First, you have to understand which systematic are we talking about. So you apply the null test to try to find these systematics. And so then, if they are more stronger than the white noise, and in the other case, you to estimate the effect of the level of power spectrum, what you do, you simply create a simulation based on those systematic using real detector pointing. And so these are the results. This is the TT-CME, this is the half ring spectra, and those are the systematics that we consider, and you can see that they are not affecting the power spectra at the moment in temperature. So now you assess the systematic, have the maps. What you have to do is to validate your data. First, you apply a kind of internal validation to check if your data is of the quality that we expect. To do that, this is principally we set up a kind of team that is dedicated. And a lot of analysis has been performed by this team. And I mean, here you can see the power spectra, the 30 gigahertz, 44, and 70 gigahertz. And these are the power spectra of the survey difference maps and the power spectra of the half ring maps. You can see that there is something strange here, especially at 30 gigahertz, that give us the sensation that there is some still residual, side lobe residual on our maps that has not been included, the removal of this side lobe in the pipeline used for the products. This is not affecting the temperature, but we have to correct it, and we are ready to correct it, and we are now checking the results for the new pipeline that is aimed for the polarization. So then you validate your maps internally. What you have to do is to cross-validate maps between instrument, between frequency. So we did these different tests. One of those tests was to compare the power spectra in the multiple range around the first acoustic peak, removing the estimated contribution from our solid sources. And those are the results. I mean, you can see that this is the 70 gigahertz against the 44, 70 against the 30, 44 against the 30. And you can see that they are really good. I mean, there is a real good consistency between those frequencies. We then do another test to understand, okay, so now the frequency between them are correct. But is the 73 gigahertz frequency correct? So we apply some simulation, we use the Hausmann test to assess the consistency, and we didn't find any statistical significant inconsistency in this test. We then apply another test to understand if our maps are consistent, the frequency map are consistent with the map made for single radiometer or single R. And we didn't find any residual with respect to the null hypothesis. So we are confident that they are very good. So then HFI applied the same process, and they first estimate the difference of the maps. The survey difference map was being subtracted from a systematic free yardstick simulation. Doing that such a way, you have an estimation of the residual of the systematic at each beam. And this is give you an idea how much systematic is still be there, and you can treat it. High focal plane is particularly sensitive to relative gain error. This is used also to estimate a sensitivity to the side lobe pickup. So then here you have a kind of an internal test made as cross power spectrum between survey 1 and survey 2. You should note for the 142 gigahertz to 270 gigahertz that the residual are very small with respect to the binary sample variance envelope. Another way to understand if data is consistent and at HFI level is to verify the consistency between detectors. So you, check the data between detectors and you apply a correction to minimize this difference. So you plot that and you can see that they are very, very in line. This is very precise way. And the variation are only a few 2 or 3 micro K square. So then you verify the LFI maps, you verify the HFI maps. The best thing to do is to verify HFI against LFI. And this is the difference. That is, from my point of view, it's impressive because I remember that the pipeline has been created, separated by different people in a different way using a different hardware instrument. And so this is the 100 gigahertz minus the 70 gigahertz, and there's a K comparison between 70 and 100 gigahertz. And the same B structure at high latitude disappear completely. This tells you that you are doing the right way, and the instrument are the very, the data is at the same level. Another way to show it, is if you take the 143 gigahertz as a reference and you calibrate, intercalibrate common frequency, common CNB anisotropy between all the frequency, and you plot this value, you can see that all the frequencies are very near, and this tells you the consistency value between LFI and HFI maps. And you see that the 70 gigahertz is consistent with the 100 gigahertz all HFI maps at the level of 0.3%. And that is a very great result. This is the same table that Jan showed. Is the summary of the number you have in the paper. I will not discuss any number, but what was impressive to me, we didn't expect to have so good calibration certainty right now. We still have a lot of work to do to improve it, but we are really in a good shape. So I then show the 9 maps because this is our child. We spent 20 years to have those maps, and from my point of view, they are impressive. You will have here, this was a slide provided by Marco that I liked a lot. You have here the physical position, the horn, and the frequency that we are talking about. This is the 30 gigahertz. You can see at the 30 gigahertz these strange things. This is not an error, it's reality. What's happened is that during the first day of the mission, LFI, we detect strange things on our data. We didn't know. And the instrument team switched off the instrument because the first things that you do if you don't understand what's happening, switch it off. And so restart, try to understand. And this is what we did. And the problem was due to the fact that we was hit by cosmic ray, and so a gain change on the onboard memory was applied. And we didn't know. And so we lose about 1.5 days of data. And so this stripes is due to this fact. Means that there is less data there, but when we will have more data, you will not be able to see it. And the instrument team was very good to understand the problem, and so to apply a patch that was now still working. That is the 44 gigahertz. This is the 70. And this is the HFI 100 gigahertz. That is impressive from my point of view. And you see here the 100 gigahertz. 143, 200, 300. And my favorite one is the 800. That's, is very good. Okay, last slide in conclusion. So maps, products delivered at a very high quality. And consistency, as I tried to give you this message, was one of key points of our analysis of our pipeline. Now we have, the work didn't finish, so we still have a lot of work to do, because the next goal is the polarization. And polarization is harder than temperature. It's true that now we have a machine, a well, that is still working very fast. But we have to go very deep on our data. And I mean, in my mind, one of the main points will be to include the side lobe in the calibration process. So keep it out from the calibration and taking it in account when you do the calibration. Use a better beam understanding, the 4-pi beam. Especially for LFI, will be important to use the in-band 4-pi beams, because each frequency you have to, I mean, the beam at different frequency. We have to remove the galactic stroli. HFI is now working, I think they already have a working pipeline on the ADC nonlinearity effect that should be removed. That is one of the main systematics to be removed. And we have to assess the no systematic polarization as we did for the temperature. And so then optimize the zodiacal light removal. That's all.
Thank you, Andrea.
I forgot. I mean, you will see this slide a lot of times. I will put it. This is a really great collaboration.
Thank you again. Any question? Any question? Don't be shy. We have some time now. We are back on track for the schedule. No?